All right. So today is the last lecture of this course. And today we are going to talk about light, materials, shading in the first part of the lecture, and texture. And we are going to discuss this from the point of view of graphics and machine learning. So we're going to start with light, shading, and materials. And the overview of this first part is that in the beginning, we are going to discuss the concepts. We give a conceptual framework of light, materials, and shading. And then we are going to discuss how to apply all these concepts to machine learning. And then we'll have deep materials, materials that are learned and can be used in AI graphics. So we are going to use the conceptual framework that we have been using in the course since the very beginning. This is the paradigm of the 4 universes. So we have like these 4 levels of abstraction. And then you have like the physical universe, the mathematical universe, the representation universe, and the implementation universe. So for the subject matter that we are going to discuss today, the concepts are in the physical universe, you have light and matter. And then we need to model this mathematically. So we have illumination models in the mathematical universe. And then to actually apply this as a representation, we need shading methods to kind of put that to use, right? And then to implement this, we are going to have in the implementation universe polarization functions that basically are going to materialize all these concepts physically in some device. Okay. So we start with illumination. So we have already discussed illumination previously in the course. And we have seen that the illumination is the study of light emission and propagation, and involves light sources, materials, and the transport of radiant energy. But there are 2 views of illumination. One view is the global illumination, and the other view is the local illumination. So in previous lecture, we discussed the issue of global illumination. And in this lecture, we are going to discuss local illumination, because it's exactly related to how light sources interact with materials and how the transport of energy happens locally at any point of every surface of a scene, and then arrives as radiant energy at the sensor of a camera to create an image. Okay, so starting with light, light has a dual model, because we can study light either as a particle or as a wave. So the light actually is made up of these particles that carry radiant energy. So these are the photons. But these photons, they travel and they oscillate. And for that reason, they characterize as an electromagnetic wave. And then the attributes of light are exactly corresponding to these 2 aspects. So you have the energy, this is the number of photons that are traveling at some path, and the wavelengths that's related to the way they are oscillating, traveling in some direction. So here we see some light sources that are emitting photons, and then the photons kind of oscillate, but they travel at the speed of light, right? And then because they go up and down and travel ahead, they make this sinusoidal path, that's the oscillation. And then you can characterize the wavelengths, that's the period between these oscillations. And then the energy is associated with the number of photons for each of these paths. And then because it's an electromagnetic wave, we have electric field and a magnetic field for each wavelength. And then this is part of the modeling. And then here you can see that besides the radiant visible energy, you have other electromagnetic waves like X-rays and other microwaves, infrareds. And so what we are interested in is this small part of the electromagnetic wave that characterizes the visible spectrum, right? And then each color of the visible spectrum is associated with a wavelength in this continuum, the frequency that the photons oscillate, right? So this is light, and here we are going to use more the particle aspects of the light. And then we have a transmission, and for transmission, in the last lecture we discussed the radial equation for surfaces and for volumes. Here we are going to assume that we are dealing with the radial equation for surface. So we are not going to consider the participating medium. We are going to just consider what happens, the interaction between two medium. The air that we are assuming that doesn't participate, it's like the vacuum in the space, and some object that has a surface that divides the ambient space and the inside of the object. So in that sense, we are going to use geometric objects to study light rays. And the interesting thing that happens is the interface of two medium. So here we have, like, let's say, air, and here we have some other medium, in this case, water. And then, so we have two phenomena that can happen. If this medium is like an opaque surface, what's going to happen is going to have reflection. So we have the incident light ray, and then we have the reflected light ray. If the perfect mirror, it's going to, the angle of incidence is going to be equal the angle of reflected. But if it's a translucent medium like water, then we have to apply, we have the phenomenon of refraction, and then we have to apply Snell's law. And basically, we have to use the index of refraction, and then the ray is going to kind of penetrate the medium and deviates depending on the index of refraction that is proportional to the sine of these two angles. And then these are the two basic mechanisms for light transmission: reflection and refraction. And for this, we use geometric optics, and compute the directions of light rays. But then, as I mentioned, the interesting things happen at the boundary of a surface. So you need to consider the surface material. And then we have this issue of the boundary interaction. And here again, we are going to use the Fresnel equation. And the Fresnel equation is a very deep study of physics. And then one of the solutions is related to the reflectance. And the Fresnel equation relates what's reflected from a surface in terms of the angle and the wavelength. And so here we see that if there's a ray that comes at a small incidence angle, then we have a reflection that is according the amount of reflection in these directions is larger. And then if you have a ray that comes a shallow, a large incidence angle, you have the specular reflection is going to be smaller. And so there is this angle dependence. And also there is a dependence on the type of the material and the wavelength. Then we have like three basic types of materials. We have the dielectric materials that are insulating, that are translucent in general, like glass and others. And then you have the metals that are conductors. And in general, they are opaque, like copper and other metals. And then you have composite types that you have like some pigments. And then under the pigments, floating the pigment, you have like some substrate that has, different properties. And so what happens is that the rays, they can reflect in the surface of the substrate, but they penetrate the substrate and then they bounce around inside the material, and then they get reflected. And so here we see like three examples of different materials. The first one is glass, that's dielectric, insulating, and the other is a metal, that's a copper, that's a conductor, and then you have like this plastic material that you have like this plastic cover, and then some dye inside that gives the color of the material. So and all this procedure, we can study, understand what happens when the radiant energy is transmitted and scattered from some light source in the boundary of different medium surfaces in our scene. Okay, and then there is another issue related to this Fresnel equation and Maxwell equations, because the Fresnel equations are related to the physics of Maxwell equations. And then this is like here we discussed that the boundary interaction given by the Fresnel equation depends on the function of angle and wavelength. Here we see that also depends in light polarization. And so depending on whether the material is dielectric or conductor, then you have different issues, because the light in this view of the electromagnetic wave, it has like different the electric and magnetic fields. You have like this different polarizations. You have like a P polarization and S polarization, and can also be unpolarized. And you see that the Fresnel reflexes, depending on the type of light polarization, is going to get a different behavior. Like here, you see for the conductor, one stream is the P polarization, the other stream is the S polarization. In the middle, we have unpolarized that sort of interpolates between them, right? And then the same for the dielectric, but see that the behavior is totally different from metals and non-metals. And here you see the effects of the reflections for a conductor and a dielectric, right? So the reflections are different. So these are very intricate phenomena that are related to physics of, illumination and materials. And then the other thing that happens is that the amount of light that scatters at the boundary depends on the surface geometry. And one way to study and get a mathematical model of the surface geometry is to study the microscopic properties of the surface. And then we have this model that's called the microfacet model, because basically it discusses and gives how light scatters and how much of the incoming energy is attenuated by the geometry of the surface. So, and then there is like two stream types of surface geometry. There are the very smooth geometry, where the surface is very smooth, like a mirror or like a plastic, or surface is rough, like some material like a chalk and things like that. And so what happens is that when the surface is smooth, is a total transmission. What that means that the light that's incoming light is reflected or transmitted. And there's no absorption by the medium. So there's little attenuation. But for rough surfaces, some of the energy is transmitted back, but there's an absorption. And the way this is modeled mathematically is because you have like these microfacets, and the light rays come, but they get blocked by the microgeometry of the surface, and that gives like some absorption of the light. Okay, and so this is something that is included in the reflection model for different surfaces, because You have the material, and then you have the geometry. And then you have the local illumination, and you have like illumination mechanisms. And what we need to consider is the light rays that are coming. You know, they are the wave model of light. In that sense, the light rays are going to transport the radiant energy, but you have different types of rays. There are the coherent and incoherent rays. The coherent rays, like the laser pointers and things like that, they all have the same frequency and they are aligned. And then you have the incoherent, like a fluorescence light, that they are not the same frequency and they are not aligned, they are not all in phase. And this produces different effects when you are like consider the scattering, especially related to color. And to study the local illumination, what we are going to use is something that we already have discussed here in the course, is the bidirectional transport function. So the bidirectional transport function basically gives the ratio between what's the incoming light and the outgoing light. And this is studied in the hemisphere of each point of the surfaces. We consider the illumination hemisphere, and then this proportion of the light energy that's incoming and the light energy that's outgoing is defined by this function. And because we are studying this inside this illumination hemisphere, we have to consider the differential of angle. And here we put this cosine term when we do the integration over the illumination hemisphere. Okay, and so all this gives a model for the light propagation and the transmission. And this is a data-driven model, and we call like this render context. So here we are considering the three main aspects that interact in light shading materials. Is we have light sources, we have objects that have some geometry and some material, and we are interested in what is seen by a camera. And then later on we are going to discuss shading. And so one important thing to consider that was already mentioned before in the course is the reciprocity factor. Is as the Helmholtz reciprocity, that if you have a light path that goes out from the light, arrives at the material, is reflected, and arrives at the sensor of the camera, the radiant energy that goes and travels the flux of radiant energy along this path doesn't matter whether we are considered from the light to the sensor or from the sensor to the light. And this is very important for some computations, right? And what we want to compute is this, render context that is data-driven, because we can consider, we want to know the color of this pixel that's associated with a sensor of the camera. Then we can follow the rays backward to the light, as we discussed when we discussed path tracing. And for shading, we can assign values to light energy on the surfaces and project that on the image. And there's a way to do that. And so for this reason, an important thing to study is the illumination hemisphere, because there's all the scattering that we are going to deal with. And as I mentioned, this the illumination hemisphere is what happens at each point of every surface in the scene. And you consider the tangent plane of this point and this illumination and all the rays that goes inside the incoming illumination hemisphere and goes out in the outgoing illumination hemisphere. And you also have one that is the other on the side of the tangent plane, when you have like a translucent medium, because you can go in here and go out below, or go in here and go out for the other side, right? And so to do all the modeling for local illumination, we are exactly going to model the BRDF, is the bidirectional reflectance distribution function. And as I mentioned, we have incoming ray directions, outgoing ray directions, and this is a four-dimensional function because you have the illumination hemisphere and you measure these directions by the two angles, theta and phi, related to the normal and the plane. And then this function is going to give the proportion of photons that come into one direction and go out in another direction. But this happens globally over the whole hemisphere. And so this BRDF models this function, right? And what we're interested is in the transport computation. And as I mentioned, we need to consider either solid angles or the area differential, because we can integrate over the hemisphere or we can integrate over the small patches in the surface. Either way, we are going to consider differentiable solid angles or differentiable areas. And with this, we can compute everything after we do all this integration, right? And there are two ways to represent a BRDF. One is using analytical models. So this is either a physical way to model the reflectance of a material, or a phenomenological way that considers the most important aspects. So, and in that sense, these analytical models, basically, you consider the space of BRDF functions. And then in this space of BRDF functions, that is a four-dimensional space, we put some bases. And then you model the BRDF as a linear combination of the bases. And what we need to do to characterize one BRDF is to know the coefficients associated with the bases. On the other hand, for real materials, it's very common to have measured BRDF. So we have a real material, and you measure how it reflects lights in all directions, and we have a sort of a sample data, like a table, and reconstruct this continuous function to interpolation and fitting to this data that is collected to this sampling process. And then we are going to consider both here. So in terms of local illumination models, one simple way that was used in the beginning of graphics is consider an ideal base, exactly taking the two streams of reflections, the pure diffuse and specular. And then what happens, the pure diffuse basis basically says that when there is a light ray that comes into the illumination hemisphere, that energy is spread all over the hemisphere equally in all directions. And this is very simple, and this is according to Lambert's law. And this proportion is measured by the dot product between the angle from the ray that comes from the light and then the normal of the surface. And then you have like a specular materials that the material is a reflector, but it doesn't, it's not a perfect mirror. So it reflects light mainly in the reflected direction, but it has a taper like this. And so there are many approximations for this specular basis. One of them that's very popular is Phong approximation, that you take the reflected direction and then you raise that to a power, and then you have the spread that makes the reflectance spread more like in the direction of reflections, but spreads all over the neighboring directions. And then you can characterize one material by characterizing these coefficients for diffuse bases and specular bases. Okay. And if you are going to use this measure BRDFs, then you have some apparatus that needs to take like a small material, you put like here, you have a light source, and you have a detector. And then you kind of do a very lengthy sampling process in a laboratory. and you move this light in all directions, and you move the reflection in all directions, and build a big table. And with this big table, you can interpolate and get the reflectance of any real material. And so here is work that was done in a Mitsubishi research lab, and they create a BRDF database of all sorts of material. And then you can just go in there, look it up, and apply. And then you can recognize different materials. And these are real materials applied to geometry of a sphere. Right? Okay. And then there are programs that allows you to construct your BRDFs. Like one is this BRDF lab that can deal both with analytical and measured data. And then you can design your own BRDF. And then here you select the model, and you kind of measure the coefficients. Here you see you know, the material, what happens in terms of the reflectance for that BRDF. And so see that this BRDF is specular, but also is retroreflective, because like the ray comes in one direction, most goes in that direction, but some other part reflects back in the incoming directions. And then you can render the surface with some illumination map, and then see the effect in the real geometry. And here, once you characterize your BRDFs, then you have material types that you can just select. I'll have material like this, like that. And here are the most popular material types, like you have a mirror material, a matte material, a metal material, a plastic material. And then for those materials, you just select the colors, because you know material can be a plastic, but can be a red plastic, a blue plastic. That will depend on the dye of the pigments of this surface. The metal is different, because the metal is related to the material, to different metals. And so copper is different than aluminum, and then you can measure and you have those parameters. And mirror are easier, because basically they reflect back everything, and easy to do. But there are other materials that are more sophisticated that don't use the BRDF, but use the standard model, is the BSS-RDF. Because those models, they have like subsurface scattering, like marble, the skin of people, you know, like a person, when you see the face of a person, and the person is shy and then blushes, is that because the blood is flowing faster, and then you have this red tints in the face, because the skin is a little bit translucent. And then what happens is that this BSRDF, we study not only the Fresnel transmittance and incident light surface reflection, but what happens when the array, you know, process this material, and then on the subsurface, kind of, you know, not just go, but the surface is so complicated that there's a scattering in the subsurface, and there's a retransmission back, right? And then these models are more complicated. I'm not going to discuss them here, but they're very important for some materials, like you know, representing human faces, or you know, materials like marble statues and things like that, right? And then we need to consider the light sources, right? And then there are two types of light sources: the ideal light sources and the physical light sources. So the ideal light sources, they're ideal because they kind of model an abstraction of happens to important light sources in our world. You know, the first one is the directional light, is for a light that's very distant. And then when this directional light you consider, it's like the light of the sun. The sun is so far away from the Earth that all the rays are supposed to become in the same direction. They are all parallel. And that's easier to model. And this is a very important light, because in outdoors is the predominant light source. And then indoors, a very simple light is a light of a candle or incandescent bulb that is a point light. The light emits in all directions. And from that, the light source, And usually here you have a range because the energy kind of has to decay with distance. And so here we see that up to some point, we have to kind of decay the amount of energy because it's as a local light. And then you have a spotlight that some luminaries has this because you have some apparatus that blocks the light from some angle. So the spotlight has like a desk lamp, right? That's going to illuminate only in a certain within a certain angle from the light, and also is a local light, has a range. So these three lights are model the common lights that we have in the old. They're easy to compute because we don't need to integrate the light rays because they are all come from either a point or a direction. But the real lights, they have area, and then you have to consider the light as a material that emits light. So we have a geometry, and that geometry, the geometry itself emits light. So we have area light sources, right? And then this is a model that's more complicated, but follows the same principles, right? And for the light to reach a surface, there has to be a light coupling. So as we mentioned when we were discussing the global illumination, the visibility important part in illumination, because not only the camera must see the surfaces that are reflecting, but for the light energy to come to that point at the surface, that point has to see the light, or the light has to see the point. Due to the Helmholtz process, the same. And then we need to consider the visibility from the light source to a point in a surface, and that point in a surface to the camera. Okay, and so when that happens, we say that there's a light coupling, and then there's a light transmission that transmits from the light source to the camera, right? And then there's shading because we need to actually take the geometry in the scene and transfer that to the image. And then we have this concept of a polarization function. So the idea is that you take an image and you partition the image in regions that are related to points in 3D scene. And this polarization function gives this partition, and it depends on how you are represent your scene. So the representation, we assume that we have a continuous geometry in the scene that's projected to the screen, and then you have to break this in pieces. And then depending on the geometry, this could be either surface patches, polygons, micropolygons, or pixels. And then here we see like a polygon, we see the pixels, we have a micropolygon, you have samples inside like this thing. And so depending on your shaping method, you have a polarization function that's going to deal with this. And shading is basically related to a sampling interpolation, because you have to sample what happens at some point in a surface in the scene, and then project that to the screen, and then do some interpolation to have like a continuous image. Okay. And regarding interpolation, there are different ways to do the interpolation. Let's suppose that you have a polygonal mesh that you project in an image. And then so you can do the shading for each polygon. And then this is called flat shading. You see like this effect here. Or you can have this Gouraud shading. Gouraud is the name of a researcher that devised this method, because it is a clever method that says, well, see, if your surface is mostly diffuse, then what you can do, you compute the light for each vertex of this mesh, and then you interpolate the reflected values inside the polygon, and then you give like a appearance of continuous surface. Here you see that inside it looks like continuous, right? You see, but this is a polygon because of the boundary here, the silhouette, right? But then if your surface is specular, then you have to do something more clever, because you have like a specular highlights that may appear inside some polygon, right? And so there's Fong shading. That's another researcher. His name is Tui Fong, and Guro is Andy Guro. These are researchers that did a PhD at Utah University that I mentioned here at the course earlier. And the Fong shading method, what it does is computes the normals for each vertex and actually interpolates the normal to pretend that the surface is not polygonal, but smooth. And then for each point, use that normal to compute the shading, and then is interpolated in that way. But this, what you compute in the surface with illumination and then project to the screen, this is in radians. And this has a very high dynamic range and is not adapted to different displays. And then we have like these coloring functions that do tone mapping that converts radians to actual colors in some device. And depending on the device, it has to do some conversions based on the color space of the device. Okay. All right. So this gives you a very broad view of light shading in materials. And now we are going to see how we can use this with machine learning to learn real materials using deep neural networks, right? And this is work from SIGGRAPH Asia 2020, like 2 years ago, 4 years ago. So, okay, so I'm first going to discuss material generation, and then I'm going to give an example of this research. It's a paper called Match, that is a differentiable material graph for procedural material capture. Okay. And so, but this first part of material generation is going to be broader. We're going to try to situate you of different machine learning methods for acquiring and learning real materials. Okay, as we have seen, we have an object in the scene, and this object access has two aspects. Has the geometry that's related to all the geometric computations, and some involve lighting and illumination, but you have the material that actually gives the visual properties that are of reflectance of that object. And so we are going to concentrate on materials, okay? And in that sense, the same way we model the geometry, we have to model the materials, and ideally based on real materials. So we have this issue of material acquisition. So in this real scene, you see the number of materials we have. You have plaster, leather, fabric, stone, polymer, metal, wood, etc. Like here, this book not only has material, but has a texture. That's something that we are going to discuss in the second part of the lecture. Okay? And then how to do this using machine learning. There are two classes of methods that are complementary. One is you measure the material using a per pixel based approach to acquire the material. And the other is a procedural. Basically, you learn some shader graph. That's a procedure that's going to implement that material. Okay, and then the per pixel based, you can divide in two classes, subdivided, right? One is like a full measurement that's similar to what I mentioned earlier, to acquire materials that you have a big apparatus to measure some material. But in this case, is an even bigger apparatus to measure an object, right? And then you put the object there and you kind of measure that, right? And then there are lightweight methods, both for procedure and per pixel, where you have some sensor, like a smartphone that has a camera, and then you capture several images, and you measure the material more or less the same way we reconstruct the geometry of a scene using multi-view reconstruction, right? And so we are going to discuss this here. So the full measure for per pixel basis, these are two examples of this apparatus. This one is the Stanford spherical gantry that can be used to collect material patches or material for real objects, right? And here, this gantry is similar to the design that I showed before schematically, because you have like a lamp that kind of moves around this arc, and this table rotates, and then there's the camera that moves around another arc, and so everything rotates, and so it's less expensive, but you have to calibrate it very well. But you have like this dome for University of Bonn, that you have a lot of lights and cameras around the dome, and then it's easy. We need to calibrate the sensors, but then the mechanics they are fixed there. So you put something inside, and then you get from both of this full measure per pixel base, you have like this measure reflectancy images. Then you apply that to different materials, and depending on how you do it, you also get the microgeometry. For the lightweight capture, we have already seen the mechanisms to do this for other image processing, because basically you have these patches, and then you have a convolutional neural network, and using inverse rendering, differentiable rendering, you want to kind of reproduce this material, real material, synthesized by the self training. That's instead of use differentiable rendering to do self-supervision, and then you teach this neural networks to synthesize the material, and synthesize the material with different components. You see that here you have like the diffuse part, the specular part, and everything. So these are components of the material, right? And this method is very good. A lot of papers in this area. So it's lightweight, it's fast. You don't need any specialized equipment. And once you have the system in place, it's easy to do, right? But it has some issues, because you have a fixed resolution. You cannot edit the material, and it's memory inefficient, because you have a big neural network to do this. It's no editable, because you cannot change the parameters, right? And then you have the procedural base, that what we are going to focus now, because instead of having a neural network that's going to learn to synthesize the material, we are going to have a procedural representation that's going to be a procedural graph. And this is actually something that is used in graphics, because it's a shader graph that takes all the illumination into account, and the material is represented by a function in this shading graph. It's like a language to do shading. And then we want to learn a program in this shading language, right? And so it has all the benefits of the this per pixel based lightweight capture, but doesn't have any of the disadvantage, because it's resolution independent, is editable, is memory efficient, is also tileable, because you train to tile this within a domain of a surface, right, or some object. And so we are going to describe this paper that's called Match. So it's differentiable material graph for procedural material capture. The difference from what we have seen before is that here, instead of using a differentiable rendering, we need a differentiable material graph to do machine learning, right? And so this is the whole scheme. We have this lightweight procedural material capture that takes as inputs photographs, patches of the material, and then you have a library of templates for shading graphs, and uses a k-means method to select from that library the shading graph that has the structure for this the type of material. Like you see, like this material in the middle is totally different from the material on the top and the bottom, right? And probably it's going to be a different model when you select. And using k-means, you select material. And so here you have the gap, the graph, right? And then you use a CNN to train the parameters of this graph to predict some texture. But then it's the parameters of the commands of this program, right? And then it generates the maps and use a loss function that's going to compare some input photograph with the predict texture. Just to make it clear, like this, model that was selected is compatible with this input photograph, and this is the predict texture. And this is compatible with this other one, and so, right? And then the representation, as I mentioned, is a procedural shader graph. So what's a procedural shader graph? You have all these nodes, and then it also does this on-demand computation because you have these elements, and then when you compute something, goes through the graph and generates the output. And here, the advantage of this method, as I mentioned, is that first is resolution independent, then is stylable, is multi-resolution, and is editable. Okay? And this work was implemented in the Adobe Substance that's used in the industry for games and avatars and so. And so this actually is a computer graphics work with machine learning that's really useful. It's used throughout the industry in all areas, design, entertainment, everything. It makes a difference. But the main thing is that we have to consider a differentiable procedural material. So it's a material that is not a simple shader graph. It's a shader graph that we can do gradient-based optimization. We need to do back propagation to optimize and learn the parameters. And here is the scheme for that. We have all these differentiable paths. We have some inputs, some unknown that you need to compute, and then you have the output. And then here we have only one in this graph. I have only one element that's non-differentiable. That's source of randomness that you don't consider when you are training. And then when you train, you can include some randomness to give more variety to your results. And here are some examples of what we're learning with this, scheme, right? And then the important thing here is that you have these nodes, right? And then they all need to be differentiable. And here you have classes, different classes of nodes in this graph. You have the generator nodes that are inputs, and the inputs are usually either noises or patterns. And so depending on your material, you can have a pattern or a noise depending on how structured the material is, right? And so here in the graph, you see where the noises or patterns are. These generator nodes are indicated here in yellow, right? So they generate something that goes to the other nodes, right? And then the other nodes, they could be either atomic filter nodes that do some kind of conversion, right? Like some blur, warping, blending, change the color and things like that. And then you have non-atomic filter nodes that combine things and do some computation, like this edge detection. And this one can be very complicated. Like this edge detection, it's like this small nodes. And so this is big graph here, okay? But they are differentiable. And then when you are modeling the pattern, you see this is the graph, like a big graph. And then this is a material that synthesizes wood, right? And as I mentioned, this is editable. You can change the color, you can change the reflectance and things like that. And this is important in practical applications, right? And here are some results, right? So here are high resolution material synthesis. So here we have the patches, and you have like the material, folder details, and blurry details, right? But it's not perfect. Can be optimized. There's some limitations. Like one limitation is that you take the graph template and you cannot optimize the graph structure. You cannot change the template. So if the template doesn't have all the expressiveness for your material, then you need to create a special one, right? And also cannot optimize the generators entirely related nodes. So you have the different types of noises and patterns, but it doesn't optimize that. That's fixed. And some materials cannot be converted. And so here we see some examples of not failures, but the limitations. So we have here the target, and here we have the original, and the optimizer doesn't resemble the original. And so these are some things that we cannot do. And they also said that the future work, they want to fix that, to implement a full version of this atomic filter nodes to support optimization of generation nodes and conversion of monograph, and have this search for material graph architecture. So we could actually search for the best template, not just writing means, but I have something that with mutations to get new templates using this architecture search. And so this is a good example of useful work that does machine learning in the context of materials. Okay, so now I'm going to pass to the second part of the lecture. I'm going to discuss texture. And texture is very important because besides the way the surface reflects the incoming light energy that change the appearance, you have some things that are like imprinted in the objects, and some things that you can use mappings to put in the context of the visual information for image synthesis and understanding, right? And so that's texture. So we are going to discuss texture mapping. And so we are going to discuss in the second part of the lecture the concept of texture mapping. And then we are going to discuss neural 3D textures. So textures that are created and learned using neural networks. And so starting with texture concepts and uses, we have this concepts of texture mapping. Basically, we have like spaces that are going to manipulate the mapping process. So we have the object space, you have the texture space, and you have the attribute space. And for mapping some texture in some surface that has some attributes, we need two functions. We have a texture functions and a mapping functions. And that's the reason it's called texture mapping, because we combine texture with mapping, right? And what happens is that the mapping function maps the space of the object into the space of the mapping of the texture, right? And then the texture function maps the domain of the texture into the space of attributes. And in the end, when you do a composition of the mapping with texture, that you have texture mapping, is T composed with G, and then we are mapping the object to attributes, and that's the texture mapping. And so to study texture mapping, we have this diagram that basically is the footprint of the blueprint of texture mapping. And what we're interested in the composition, T composed with G, and here we have the texture function and the mapping function, and you have the composition. And with this, we can understand the main issues related to texture mapping. And the main issues are, one, the object representation, how we are going to represent the object to do texture mapping. Then is the domain dimensions of our texture. And then to devise this the mapping function, we need a coordinate generation to associate points of the object with a texture coordinates, right? And then once we have that, we have the texture representation that maps some attributes, and you need a representation for the texture itself. And then having all this, we finally need the composition, the different uses of texture. And we're going to, characterize how we choose these representations and the domains and things like that. And the most important thing here is in the middle, this asterisk, that is to do all that, we need to do sampling and reconstruction. And so we are going to discuss these 7 issues related to texture mapping. And the first is the object representation. And so the object representation basically boils down to the surface representation. And as we have seen here in the course, we have basically the parametric representation and the implicit representation. And when you have the parametric representation, the most natural thing is use 2D textures. And notice that the 2D textures is basically the inverse of the parametric function, because the parametric function maps points of the object to the space. And we, for the texture, we need to do the opposite, map points from the space to the texture. An implicit function is a function of the ambient space, and then usually use a 3D texture, because basically what we do, we put the texture in the 3D space and carve the shape of the object. Like you have like a block of marble and then you carve a statue. And so in that sense, G is the identity. And then you have like the domain dimension, because the dimension of the texture can be the same as the dimension of the surface of the object, or can be higher or lower, right? And so when the dimension of the texture is the same as the dimension of the object, then you have a case of parameterization, as I mentioned before, right? But then when you have a dimension of the texture greater than the dimension of the object, then you have a question of a projection. You want to project that into the object. And then when in the dimension of the texture is greater than the object, you have insertion. That's the case of volume texture, because basically we take the restriction of the points in 3D to the surface, right? And then usually the texture space is either 2D or 3D. And the natural thing is that when it's 2D, use a parametric, and when 3D is used implicit. But can be different, can do other tricks depending on what kind of things you are doing in the texture mapping, because it's not just to attributes on a surface of an object, it can be to other properties in the illumination computation, like computing reflections and things. You can do textures, for instance, in the illumination hemisphere with angles and things like that. Okay, and then you have like this coordinate generation that relates to computing texture coordinates. And so these are different types of mappings. So we have like 2D mappings, like a object parameterization of decal, that's a projection, or 3D mapping that you need to compute, consider the local object space with the texture space. And there's an important thing here, that's texture distortion, because usually the texture you model in a planar domain, and the surface is curved. And then when you do this coordinate generation, you have to minimize distortion and compensate for distortion, so that things appear to be, embedded in the surface, not like distorted, right? And distortion also gives like some artifacts in terms of resolution, things like that. And then related to the type of information that you are doing the mapping, we need to consider the type of attributes. And then you have like attributes that are related to modeling objects and surfaces, and then attributes that are related to the rendering, to compute illumination. And then, so for modeling, to map things on texture on surface, we have scalars, vectors, and colors. So scalars can be one object that's parts, one material and parts of another. And then you are going to put like a coefficients, let's say, how much of that material is in different parts of the object. Then you can model geometry, like you can do normal mapping, bump mapping, and things like that. And then you can map colors, because you can actually imprint textures, like images, like glue some label in the surface of an object, right? And then for rendering, you have other things like angles and radians, because we discussed here when we discuss path tracing, we had like photo mapping. So photo mapping does texture mapping for radians. And then some computation that you do in the illumination hemisphere, you can also use mappings, and then you are going to map the angles. And so these are the types of attributes, and the values are related to what kind of thing you are doing, like surface attributes, geometry, displacement, density, and other things, right? And finally, you have like a texture representation, and then you have models for texture. And you can model this texture in a functional way or a procedural way. So the functional way, we try to reconstruct the textures using a function that does some interpolation of values that are sampled in a regular pattern or a sparse pattern. In a procedure, you usually have primitives and an algebra, and then with these primitives, they generate what you are going to convey with the texture. And also, the texture function can be computed or measured, because if you sample the texture and put in a table, you have like the measured data, then just look it up. But if you have like some procedural texture, or even something that you are doing some computation, like a shaded graph and things like that, you can either pre-compute some things, but you can also do laser evaluation, because there are some parts of the texture that if you're not going to use for an image, you don't need to do it. And then with laser evaluation, you compute when you need and you store in a cache, right? And then for this first part, the functional texture model, we are going to do a Pierce model. And the main elements, as we mentioned before, they are the surface representation that can be parametric or implicit, the attribute values, and the texture dimension, right? And here are two examples. For 2D texture, we have our graph, we have the object, the cylinder, we have the texture, and you have the attributes that are colored, right? And then for this coordinate mapping here, you have this function T, that's the inverse of this parameterization of the cylinder that maps the image on the cylinder. And then there's a different one that if you have a implicit surface and then you want to sort of like project that, you can do a decal projection. And then instead of doing a parameterization, you just project this on the surface, and then kind of it's like a slide projection that projects that onto a surface. And there are different types of projections that are also good for 3D textures, right? And then when you have like 3D texture, volumetric textures, what you have is, like I mentioned, you have the texture that define the whole space in this cube U, and then you carve the surface inside by doing a restriction of the points of the surface to the points of the curve. And so here you have examples of like wood textures, like you have like a branch of a tree, and then you cut this wood pieces, cutting the material, the solid material, right? So this is also called solid texture. And then for procedural texture models, we have an algebra for texture generation. And that algebra is going to be expression language. And similar to the shader graphics, we have the data sources and composition operators, right? And also we use this concept of patterns and noise. And so here I'm going to discuss this noise-based textures that is important because thus a controlled randomness. And as a note, This is the PhD work of Professor Ken Perry, professor here at NYU, and this basically changed the way people use this in the industry, and actually he won Academy Oscar for that, for the contribution for visual arts and entertainment. And so I'm going to discuss the principles of the Perry noise. And the idea here is that you have a noise source function, but smooth, correlated, and band limited, and spans the Euclidean space, could be Euclidean space of dimension 1, 2, 3, 4, right? And then you have the composition of operators like sine, absolute value, multiplication, division. And so for the definition of the noise, as I mentioned, you have a controlled noise because you have different scales with different resolutions. You have a blur on that. And then what you get is this controlled randoms at different resolutions. And then you have composition because you can add noise at different scales. And you can do this using a fractal principle, the self-similarity of different scale, 1 over f noise and things like that. And then you get like this much more complicated noises. And to really simulate the phenomenological real materials from nature, we do modulation, creating these effects like turbulence and other types of modulation, right? And then with these elements, you can generate real things like marble, fire, ocean, and this is a type of phenomenon that is a natural phenomenon, and it's difficult to model otherwise, right? And so, for instance, to generate marble, you take this noise in 1 dimension, and then you take this modulation thing, and the result is like this marble base with the veins and things like that. And this actually here, I'm giving a 2D example, but this is a 3D material. So it's defined in 3D space, and this is object that takes the values from this texture. And similarly to ocean, clouds, mountains, fire, because it's very good to model fuzzy things, right? Okay, now we are going to discuss the uses in rendering, because not only we want to model the materials, but we want to use mapping in the rendering process. And as you have seen, we have to do this forward and inverse to do differentiable rendering. And so we have like a texture mapping, we have bump mapping, we have environment mapping, and we have shadow mapping. So texture mapping basically assign properties for different points of an object, like color, opacity, material properties. And typically there is a color or densities or scalars, right? And then bump mapping, they map geometric properties like the surfaces or perturbations and things like that. And the environment mapping, they map what to be the reflected properties of some material, consider the environment. And that's another concept, as you have like illumination map. You can model the main lights from an ambient using a 360-degree image that emits radiance from this, that models all the incoming light energy to a point. And for distance things, this is a very good model. And so in that way, you can model reflection and refraction. And then, as I mentioned, the visibility is very important for illumination and shading. And one thing that you can do to make the computation of visibility for light sources is do shadow mapping, because consider the visibility from light sources. And so I'm going to give examples of this. So here, texture mapping, we are mapping some materials into these 2 rectangles. So this is a brick wall, this is some other material, right? And then here we are going to use a parameterization, latitude, longitude, to map the omnidirectional image, a rectangular image on the sphere. So you have the globe with the right texture, right? And then the bump mapping it maps perturbation of the normals in a surface. So this is perturbations that change the normal when you compute the illumination. And it's very effective to model intricate details in a surface. And then you have the environment mapping that, as I say, it models the reflectance of an object. And then we consider that you have like a environment mapping that's a big representation of the ambience for the light that's coming from all directions. So that would be like this. And then you have a surface, and you want to model for any point that are seeing the surface, what is the radiance that comes from the reflected direction. And depending, basically it's very simple, because when you do this mapping, you compute the reflection vector, then they look up the direction in this environment map. And depending on how you model this, you can model a perfect mirror or like a specular brass teapot or things like that, right? And then there's shadow mapping. Shadow mapping is more involved, because what we want is to know if the light sees the surface, right? But then what we have is what the camera sees. And so here we have the elements, because you have, without the shadows, we have this image that has no shadows on the right left side. And then we want to put the shadows that is underneath. And for that, we compute the depth buffer from the point of view of the camera. And then we compute the depth buffer from the point of view of the light source. And then what we do, we kind of project from the image to the light source and see if the distance of a ray to the object is blocked by something that is in the depth buffer of this depth buffer from the light source. And this is what the light sees from that position of the scene, right? And then with that, we can compute shadows or even project some pattern if the light was like a projector, right? And so then you have like some modulation image, and then you do some blur, and then you have your image with shadows. And this is much faster than doing ray tracing and everything. And that has been used in the industry for a long time. Now it's not using so much because we have like real-time ray tracing, but it still is very useful. Okay, and so just to finalize, I'm going to talk about neural 3D textures, how to learn 3D textures with neural networks. And I'm going to describe this work from CVPR 2020 that's going to learn a neural 3D texture space from 2D exemplar. And this is important because you want to learn a 3D textures, but from a 2D patch, 2D exemplar. And here we are going to use also this noise-based principle. And the idea is that you have input a 2D texture, it's captured by an implicit field, as we have seen here previously in the course. And then you can sample this new texture at any resolution, any shape, and has all the same qualities as the previous work that you saw for materials. Like have a continuous domain, you can interpolate, it's computationally efficient. And so we can compute this using like a cell phone, right? And then you have all your exemplars and have a space of textures, and then you can use those and even interpolate between them with a language similar to the parallel noise, right? And so this is the architecture of this network. And here you see that you have a kind of encoder-decoder, but with noise in the middle. And so, and this is a coordinate-based neural network. So you have the exemplar that you are going to compare with the generator, but you want to compare in statistical sense, because we don't want to model this texture. We want to model the statistical properties of this texture that is going to consider some randomness in the noise model. And so you enter the position, X and Y, and then you enter the exemplar, and then you have this encoder that's going to have a latent code here, and you have a translator that's going to take the latent code and generate some transformations. That's going to be the input of a noise function. And then for the noise function, we have the transformation, the coordinates, and the parameters. And then this transformation is going to generate multi-resolution texture noise. And then you have the decoder that's going to get the noise and this encoding value here. And the decoder is going to generate a texture and compare with the exemplar in a statistical sense. And it's going to be optimized in that way. And so the first part is this related to noises, this part here. And so you have the coordinates, and then you have a multi-resolution texture, and then you have like these transformations to create textures with different warpings and things like that to synchronize things. And then you have noise, and then you have like these parameters that are going to be learned. And then from here, you combine this with the translator that's in this H function. And so here you have the parameters that are fixed and the parameters that are learned, right? And then you have this Z that was generated by the encoder. And then you have like these parameters that you are going to select certain transformations here. And you are going to learn these transformations. And then you have this parameter that is sort of coefficients that are going to model in a fixed. And then for training, what you do this sort of slicing, because you take different slices and you compare the statistics of different slides with the 2D exemplar. And then in that way, you learn this whole system, and it's very effective. And here is a result of the comparison. So here you have a wood, you have grass, and then here you have pedaling noise. You have a texture that run convolution neural networks, and this is what's generated by this method. And you see that this method is the most natural compared to the real textures, and it's also like a very lightweight after you train it, right? And here we have a reconstruction of different exemplars with doing different types of resynthesis. You see that you capture the diversity of the material because each resynthesis is statistically the same, but visually is different, right? And here is applied to solid texture. As I mentioned, you can combine different textures in different ways. And you see that because the solid texture, we don't have these problems of, discontinuities or mapping. Then you basically has a texture in space, but you don't need to represent it. It's just a neural network. Okay. And as I mentioned, you can interpolate the different types of exemplars and have a combined textures for more variety of textures. All right, that's it for today. And that's it for the course.